Swayam Prabha. Digital India. Educated India.
So you'll always write it out as VFG, and meaning that it is VG minus VF, and this will be a positive quantity for you. And then how you would use this is, again, going back to the equation for specific volume. So V is 1 minus X times VF plus X times VG, which if you want to rework in terms of VFG, you can just see that the first term is nothing but VF here, and then you have X times Vg minus Vf, which is nothing but Vfg. Okay, so you get Vf plus X times Vfg as your V, and similarly you can write your expressions for H and S and so on. Okay, so just for the sake of completeness, we have just shown you. This is to emphasize, if we have to go back. So again, we are looking at a TV diagram. And now you know that if you are at any state 3, okay, knowing the states at 2 and 4 and knowing the quality, you can find out anything in between. Okay, any quantity, any property of interest in between 2 and 4. Although it's a busy slide, it is actually very straightforward. The ideas in this slide are very straightforward. Now let us just, so here I'm going back to the slide and saying that we have talked about PT and TV. So we are essentially introduced 3 variables, P, T, and V. Now let us look at a 3D plot of when all these 3 things are there. Really speaking, this is not required, and it is quite, I mean, it looks somewhat complex. But I mean, for the sake of completeness, again, because a lot of textbooks, etc., introduce this. So I'm introducing it here for the sake of completeness, although I don't see too much value per se that gets added by looking at these figures. So the bottom line is that if you tend to get confused about this, you can ignore it. Okay, these next 2-3 slides, it is not very important for your understanding. Okay, I'm doing it for the sake of completeness. So here we are putting the 3 axes, P, T, and V together. And if you do that, you will start seeing certain things. I mean, from this view, for example, you will see very similar to your dome. So let me just introduce the various regions which are there. Okay, first. So in this figure, at least they are shown by different shades. So you can see shades of green or blue. And you can see that this is one region which is shown as the gaseous or the vapor phase. Then you have the liquid phase using this region here. Then you have the liquid and the vapor coexisting, shown as this region here. Then you have these, let me go to the solid first. So this is my solid, okay? And then you can see that between solid and liquid, just like you have between liquid and vapor, we have this 2-phase region. Similarly, between solid and liquid, you will have this 2-phase region, which will be essentially ice melting or water freezing. So of course, it does not happen instantaneously. Again, just like you have a quality parameter here, you can have a quality parameter here as well. And then we saw the sublimation line, which means that the gas can directly change into vapor, into solid, and vice versa, solid sublimating directly to vapor without going to this liquid phase. And that's what is this. And of course, there will be an intermittent thing that you would see, which is the solid vapor region. So these are the 3 various regions that you see. Now you can start putting things together. But before we do that, although this looks like a solid thing, let me just understand whether this is a solid that we're talking about or we are talking about a surface. So this entire thing, this is a block that we have to worry about, or this is only the surface of this block that we have to worry about? And how do we resolve this question?
So in essence, because we were talking about a pure substance and it will have only, like, let's say if we're taking it's basically only the surface that we have to be
Correct.
worried about.
Correct. That's right. That's exactly right. And how do you justify your answer?
So assuming that this is a solid, so let's take this black line which is on the screen, or like one of those lines, at a constant temperature, which means that you will get this area, which means that for a given temperature,
Okay.
that one pure substance can take like a lot of different pressure
Yeah. So let me
points at the same volume.
sorry. Can I just cut you in? So basically, what the simple way to look at it is, because we are saying two coordinates are enough, two properties are enough to describe everything else. Everything else gets fixed. Two properties, when you fix, everything else gets fixed. Okay. So my argument is that if you fix x and y, your z becomes fixed. Okay. These are the three properties. So the moment you fix x and y, your z is fixed. Okay. So that's the way I look at it. Okay. So I'm just cutting you so that, I mean, it can, I mean, sometimes we get confused. I mean, we just don't want to confuse. I mean, your argument may be clear to you, but putting it across may become sometimes difficult. So I will just put it as that x and y, for a given x and y, there is a unique z that you are going to have. And then if you change your x or y, your point, then your z is going to change. And of course, the 3 points together will describe the surface. Okay, so that's one way. So it is only a surface. You're not looking at a solid. So that means for a given x and y, you cannot have multiple values of z. So you will not have a solid, because for a solid, you would have xz1, z2, z3. And of course, combining them, you will get a solid. But here, we're not going to have that. Okay, so that's the way I argue. So we are only looking at the surface as the first thing which is clear, and the various shades as we are given are basically demarcating the various regions. Now, so now when we had looked at 2 points in my PT and TV diagram. So we can try to locate these. So you can see that earlier we had the liquid vapor region. And as we said, that as we keep on increasing the pressure, okay, you can see that this region is shrinking and ultimately becoming a point. And this is my critical point, the C, which was marked earlier. And this is actually a point even when we look at this 3D view. Whereas when we go to the other side, the T point, the triple point, you can see that this region, again, the region where you can see my cursor, is the liquid vapor region. And then at the bottom, you have the solid vapor region. So you can see that at this line, so this is one region which we have the coexistence of liquid and vapor. And then we have this region which we have the coexistence of solid and vapor. So when you look at the boundary, which will be a line intersection of these two surfaces, you will have a line intersecting. This line would essentially have all the three things together: solid, liquid, and vapor. And this is your triple point earlier, which we were saying, but we are now saying that this is not really a point. This is actually a state that you can also get. And therefore, this is a triple state that we should have. We should call it as more correctly. So C, so summarize. So we saw 2 points, C and T. So C still is a point, but T is not really a point. It's actually a line. Okay. We were getting it as a point because we were taking a projection of this line, and our line was just orthogonal to our view. Okay. So that's one thing that you can see from this solid. The other thing you can see is, of course, you can try to take two projections. You can have PV axis and just see how the things would look like, the solid would look like if you just have a P and V plane, or you can go to a PT plane, or you can go to a TV plane. Okay, so we have seen the other two planes. Now, if you want to just look at the PV plane, which is reasonably straightforward in this case, you see this dome, you will see this vapor, and you will see the liquid here. So you can remind you, this is reminds you of the TV, the very similar to TV diagram that you have drawn. It is actually looking, your PV diagram is also looking very similar to your TV diagram. Okay, so that's why we have not explicitly drawn it, and you can verify it looking at the solid here. or this surface here. Now, two more. So this sort of is a description of what we are looking at. Now we can look at follow a process and see that how we are going to transit, move from various regions. So two different set of lines are drawn here. One, which is the constant pressure line. So you can imagine that the height is essentially constant here because pressure is along the height z-axis. So height is now being constant, is held constant. So you are essentially tracing this path, the green dotted curves, that's what you are going to see. And so you start off in the vapor region and we are trying to move towards a solid region. So you can see that we are, instead of, earlier we were saying that we are adding heat. In this case, you are removing heat, you are cooling down. So once you cool down the things, you again start from vapor, superheated. Now we have talked about the terminology. We are talking about superheated vapor is what we're starting off with. So we're starting off with some point here. Follow the cursor. As you follow the cursor, you get from, you are still in the superheated right now. But at some point you will hit this boundary, which is the liquid vapor boundary. And then still, if you continue with the cooling process, your vapor will start condensing. And now you have introduced the quality. You can see that the quality is 1 here. And now the quality is going to reduce continuously as you move along this line. Okay. And then at this point, your quality will become 0. You essentially convert everything, all that entire mass that you had of vapor has now been converted into a liquid. So quality is now 0. Now we don't talk about quality because quality is 0 throughout this region. So quality is essentially not a very meaningful parameter in this part now because it is 0, it just has a 0 value. And that value is not going to change as far as you're in the liquid. So you start off with saturated liquid and then you go to a subcooled liquid, and all these are subcooled liquid. And then you come to this point, which is now at the interface of the solid and the liquid. So as we saw that there was some amount of ice which we saw some floating ice. And then as you can imagine that as we keep on freezing that further, cooling that further, more and more water is going to freeze. The amount of water that I'm going to be having is going to reduce, and the amount of ice that I'm going to have is going to increase. So again, you can define how much amount of ice solid versus how much amount of liquid is going to have using a quality parameter, which is going to be applicable in this range. And then ultimately you will have all solid. So, and then, so quality will be either 0 and 1, depending on how we are defined here. Of course, this is a different quality than the quality factor that we have defined here. Okay, so then we ultimately get into solid, and so that's essentially the entire passage, entire path that you would take, right? Now, if I increase the pressure, so I essentially go to a different height, you can see the whole process, whatever we have just described, will repeat. And this two-phase region here is going to reduce, which is between the liquid and the vapor region is going to reduce. And then if I increase the pressure further, and essentially I'm going to trace this path, and then you can see that if I am now above the critical point, then the pressure is above the critical point, then I'm not going to have this transition, this smooth transition, or this separation of the phases between the vapor and the liquid, and I will change from the vapor to the liquid directly. Okay, because now we are in essentially the supercritical state. But then, of course, you will have the transition from the liquid to the solid, and you will go to the solid. Okay. So essentially, that's the passage that you would take. Now we can talk about another passage where we start off with, I mean, you can essentially, this is not very clear, but you can essentially get into the vapor can change directly into solid. Essentially, you will pass through this state and then you will go to, so maybe if you travel a path like this, Okay, at this pressure level, you start off some point here. Okay, a point here, and then you keep reducing the temperature. You will see that you will now cross the solid. Uh, you will essentially get into this part. You will essentially start getting solid, and again you can have a quality parameter which will define how much solid versus how much vapor you have, and ultimately you will get to your solid and to complete solid here. And this is your sublimation process. So this is essentially the description of the solid that we are. I mean, I keep saying solid because it looks like a solid, but we have already said that only the surface of the solid is of interest to us. And I mean, again, I don't want to confuse you, but this is just to sort of the other figure, again, for the sake of completeness, I'm putting it. Just like in the PT diagram, we saw that either we can have, when we have the liquid and the solid line separating, we can have either a positive slope or a negative slope. Okay. So earlier we were doing it for a positive slope. And if you do it for a negative slope, this is what you would get. So this is for substances which expand on freezing. Okay. So for that, you will see that the phase diagram becomes something like this. Okay. Again, if you just sit down and figure it out, it is not very difficult, but it is not really, as I'm saying, I'm not trying to get into the details. It's just that things will expand, and therefore the specific volume will start increasing now with a reduction in temperature, and therefore you will get this part, things essentially curving back on itself. So essentially that's the what we would like to discuss about the P, V, and T diagrams. When you have all three of them and you have a sort something like a 3D figure like what is shown. So again, as I said, if it starts getting overwhelming because it's a 3D plots, uh, we don't have to worry too much about it. As far as we are clear, essentially you can really work with only one of these plots, and TV is going to be a very good option for you. Okay, and for the sake of completeness, again, we are going to introduce other plots as well. Like you can have a TS plot. Now we are introducing a new property, entropy, which we have not formally introduced yet. But because we are talking about charts, okay, I'm just going to show you other charts which one can refer to. One can use the calculations. So either you can look at TS chart, which is what the way it looks like. It looks like what is shown here, and you can identify the region like vapor on the right, the saturated or the two-phase region in between, and the liquid on the left. Okay, so in some sense, it is a very similar, the regions are very similar to your TV diagram. But when you can look at other quantities like pH, okay, it will look like this. Again, I'm doing it for the sake of completeness. I'm just repeating myself here. You can look at any of these diagrams and you can work with any of these, whatever you are comfortable with. But it's good to have at least one diagram in your mind so that you are able to differentiate the various regions clearly, and something is given, you know how to do the calculation, what state you are looking at. Okay. And this again, this is the last such diagram that we are going to look at, which is the HS in the enthalpy and the entropy. So this is a more non-intuitive, and enthalpy is non-intuitive, entropy is non-intuitive. And at least earlier you had one axis which was intuitive, temperature. The other one was not that intuitive, entropy. Here you had pressure, more intuitive, enthalpy, less intuitive. And here you have both non-intuitive, enthalpy and entropy. Okay, but as we go along, you will start getting more and more comfortable with these quantities. Um, and it's just to show that the various regions are demarcated here. You can see how the various regions are. And again, it will help you form a mental picture. But what we'll be working with is actually a steam tables, okay, because reading numbers from so these are good to look at. It is good to give you an overall sense of how things are. But if you want to really do a calculation based on these charts, it becomes very painful because you have to uh, read very, very carefully, and it is very, very difficult to read anything to decimal places. So we will rather go to a table where things are tabulated nicely for you. Of course, the difficulty lies with these tables is that you miss out on the overall picture. So that's why it is good to have the overall picture through the help of one of these charts. And then we go to a table and do the calculation based on these tables. So you'll have to combine your chart. And as I'm saying, you don't have to keep all these charts in mind. Keep one of the chart in mind. And my favorite is TV. So I will always refer to this in my mind, this TV chart. Okay. And this TV chart, once you have in mind, and you have the tables in front of you, hopefully you will be able to do the calculation and you know what region you would be realistically lying, and you should be able to do a calculation based on that. So we will stop here.